Hello and welcome back. Let's learn how to graph. For this video, we're only going to have one example because this is going to take very long. This will probably be one of my longest videos. But to graph, this is definitely an application of a derivative, another application of the limits as well. There's a lot of stuff here, but let's get into it. And I even need my sheet here to tell me what to do first. So first, we're just going to find the first derivative of this. So dy over dx is going to equal, well, we're going to take x squared minus 2 and differentiate that, so that's just going to be 2x times our regular bottom, x plus 2, minus x squared minus 2 times our derivative of this, which is just 1, so I'll just get rid of that, over the bottom squared, x plus 2 squared. So that's our first derivative. Now, we need to figure out where does this equal 0? So where are the critical points on this graph? Where is the slope, the tangent line, flat like this? So we're going to set this equal to 0. That means we can bring this over, cross multiply, and that's nothing. We're going to expand this. So we've got 2x squared plus 4x minus x squared plus 4 equals 0. And that's going to give us x squared plus 4x plus 4 equals 0. Sorry, that's a 2. I was going to say that's factorable. I don't remember it being factorable. So there's our actual thing there. We can use the quadratic formula. I'm not going to go over that. I'm just going to give you the answers. The answer is -2 plus or minus root 2. I'm sure we all know how to use the quadratic formula. X equals -2 plus or minus root 2. And that's going to equal about -0.59 and -3.41. So that is where our critical points are. That's where the slope is flat. Now, if we were to take the function at these points, for the first one, we would get -1.17. And for the second one, we would get -6.83. So that gives us the points on the graph. -0.59, -1.17, and -3.41, -6.83. So that's our critical points right there. Let's just erase some of this, except for the derivative here. Now, we're going to ask ourselves, what is the second derivative? Now, second derivative, not super fun, but it's going to end up being (4x plus 8) over x plus 2 to the 4. And you're going to find, what you're going to find is, this is just going to, if we set this equal to 0, we're going to get x equals to -2. But, if we plug -2 into our function, we're actually going to get a value that does not exist. And so what the double derivative tells us is that the slope of the slope, so the curve of the graph, so this would be concave up if we were, or sorry, to you guys that'd be concave down. So a graph that looks like this will be concaving down. And the opposite would go for a concave up. It would go like this. A good example of this would be an exponential function. They are always concave up. Always increasing, always concave up. Every derivative is always positive. So this tells us we have our critical points here. We have our, it's going to end up being an asymptote actually. And so what we want to ask now is, what's this asymptote doing? So let's take the limit as x approaches 2 from the negative of x squared minus 2 over x plus 2. And that's going to give us the limit as x approaches 2 from the negative of 1 over x plus 2 times x squared minus 2. I'm just going to take these out so that we can see that this one is going to give us negative infinity. And this one is just going to give us 2, because 2 squared minus 2, 4 minus 2 is 2. 2 times negative infinity is negative infinity. So from the left side of this graph, it's just going to shoot right down to infinity like that. Okay, let's take the right side. The right side of limit at the same point. And all we're going to get is positive infinity times 2. And that's just going to give us positive infinity. So now we know that our graph at the point x equals negative 2. So let's say this is the point x equals negative 2. It's going to go like this. Like that. Almost like a 1 over x function. Now here's a little trick for you guys with our limits. Now in your pre-calc class you may have heard a bit about vertical, or slant asymptotes. Got lost there for a second. Well, we can actually find slant asymptotes using limits, and it will prove itself to be a lot easier, in this case at least. Sometimes maybe not, but let's check it out. So first we're going to take the limit at each side of infinity to make sure there's no horizontal asymptotes, because if there's horizontal asymptotes, there can't be slant asymptotes, because then it wouldn't be a function. Or at least in that side. We could have a graph that goes like this, with a slant asymptote up here and a horizontal asymptote here, and it could go like this. That's very possible. But for this one, we're going to take the limit as x approaches infinity of x squared minus 2 over x plus 2. We can see, we can see the degree is 1 higher on the top than the bottom, so that's just going to give us positive infinity. Same for the limit as x approaches negative infinity. Since the degree is higher on top than the bottom, we're going to get negative infinity. So what I'm going to do now, I'm going to erase some of these limits. I'm going to draw a little sketch of our graph here. What I've got is I've got the point x equals negative 2, and I've got the end behavior is like this. It's like the graph's going like this. So let's do that. got it coming up, and then it shoots down at the asymptote. We've got it coming down from infinity, and then it shoots up at the asymptote. Okay, perfect. There's our sketch of our graph. Now let's hit some points right. So, what we're going to want to do now is, well, we can tell we actually don't have to do the concavity test now, because we know that if it's coming down from infinity and up, it's always concave up here, it's always concave down up here, and the only place it changes concavity is the asymptote. Well, that makes sense because that was the only solution we found to our y double prime equaling 0. We also have these points. These points are this and this because we know it must change direction to come down like this and go up like that. So we gotta have that flat zone where it bounces up, goes up to infinity, you know. So what we're gonna do now, we're gonna look for a slant asymptote because there still could be a slant asymptote going through here. Well, we know that our slant asymptote is going to be in the form y equals mx plus b. How do we find m and b though? Well, let me show you. M for us is going to equal the limit as x approaches infinity for f of x divided by x. And so for us, we can see that's quite easy. That's just the limit as x approaches infinity for x squared minus 2. And I'm just going to go ahead and distribute the x along the bottom. We get x squared plus 2x. If we divide the top and the bottom both by x squared, we're going to get the limit as x approaches infinity for 1 minus 2 over x squared over 1 plus 2 over x. And that's just 1, because these become 0, right? We all know that. So, we know we can just completely get rid of this x. It's y equals x plus b. It's looking like we're going to have a slant asymptote. So, what is b now? Well, b equals the limit as x approaches infinity for f of x minus mx. So that's easy for us. That's just f of x minus x. What's f of x minus x? Well, this is the limit as x approaches infinity for x squared minus 2 over x plus 2 minus x. We're going to multiply x by x plus 2 on the top and the bottom. It's just like multiplying by 1. What we're going to get is we're going to get the limit as x approaches infinity for x squared minus 2 over x plus 2 minus x times x plus 2 over x plus 2. And so what we can see now is we can join these fractions now to make the limit much easier to evaluate. What we get is the limit as x approaches infinity for x squared minus 2. Let's distribute this x. We've got minus x squared minus 2x over x plus 2. This equals the limit as x approaches infinity. These are going to cancel. Negative 2 minus 2x over x plus 2. We divide everything by a x on the top and the bottom. We get the limit as x approaches infinity for negative 2 over x minus 2 over 1 plus 2 over x, and that's negative 2. So that means that our slant asymptote is this formula. Y equals x minus 2. Wow, wonderful. Now we know almost exactly what our graph looks like. So now we can just do this. I'm going to rewrite these points just so that we can have a much larger graph down here. Negative 0.59, negative 1.17, negative 3.41, negative 6.83. I'm just going to take a mental picture of this graph right here. Let's write our points out. So we've got, well, the lowest x goes is 3.41, so I think I'll let it go to 5. 5, I'll let it go, I guess it can go up to 5. We'll mark our 2, negative 2. Gotta put the negative on the 5 there. This, maybe we'll let it go down to negative 10, so let this one go up to 10 just to make it proportional. So, here we go. I'll add little marks for 5s. Here we go. Let's draw our asymptotes in. Boom, 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 boom. Our slant asymptote, y equals x minus 2. Where's minus 2 on this graph? About right here. We'll mark it. Minus 2. Here's our slant asymptote. Going down like this. Whew. This is quite the task. And we've got our points. Negative 0.59, so about right here. Negative 1.17, so about here. This is our first critical point. And then we've got negative 3.41, so about maybe right here. 6.8, negative 6. Oh, sorry. I mixed up my axes there. Negative 3.41, negative 6.83. We're going to come across here, right here. Okay, let's remember what our graph looked like. We've got an asymptote coming down, boom, shooting up along that slant asymptote. Next, we've got our, clearly I haven't drawn this slant asymptote quite well because my point was below it, but slope is 0 at that point, boom. There we go. And that's our graph. This is the graph of x squared minus 2 over x plus 2. Thanks so much for watching. I hope this helps you. I could probably do one more example if anybody needs it. I could post another video, I'm sure. But yeah, thanks for watching. Hope this helps.